Okay, so, right, we're recording. So, isotopes, why we use them and what they are and what not. So, last lecture that I gave, I used this as an example of how to draw basically better slides for presentations. Okay, so what we're going to be, hopefully, going to be learning today is if we just look at this, this part of the slide here. So this is calcium isotopes on the vertical axis, and then temperature across the horizontal axis. And hopefully, some of you will have looked at this and thought, "Hang on, there's something wrong here. We're not going to believe what Alex is saying because it doesn't really make sense." So if we look a little bit more closely at what's going on here, so we want you to be critical when you look at data like this. So it's one of the things that hopefully a university education will give you is not just like the background and how to use isotopes or how to do some specific aspects of earth sciences, but actually to be critical of what other people say when they present data to you. Okay, so to be a properly skeptical scientist. So one thing that really stands out is that this graph, they've not plotted the error bars on the data, which is a bit sneaky. So they have at least plotted a representative error bar there next to the data. So you can see the error on the measurements they're making is quite large. Okay, in fact, the error on the measurements is larger than the variability that you see in the data. Okay, so that kind of means that any trend that these people are trying to pick out here, I'll just try and use the, ooh, look, we've got a laser pointer now. So any trend that these guys are seeing here is less than the magnitude of this error bar here. Okay, so that's one thing that you should always think about when you're being presented with data. What are the errors, and is the variability in the data bigger or smaller than the variability in the error? Okay. Another point on this graph is this guy here. So that's part of the data set of these data at the top here, and you see what they've done is they've plotted it with a smaller symbol because they don't want you to see it, which is kind of cheating. But you see, it definitely doesn't follow the trend that they're showing through these data up here. Okay, so that's the things that we should start to be critical about with the data. So later on in the practical, hopefully we'll see how these error bars are constructed and where they come from and what they actually mean. Okay, so another thing to think about is does this data actually mean anything? Would we expect there to be a relationship between the isotope ratio of carbonates and the temperature that they precipitated at? Okay, so first of all, would we expect there to be a relationship? Why would temperature cause there be an isotope fractionation? And secondly, would we expect it to be different at different temperatures? Okay, so I mean, we can see here that clearly the first part of the graph has a different relationship to temperature than the second half of the graph. Now, to be critical about this, we have to think, does that make sense with what we know about how isotopes fractionate? Okay, so part of today's lecture will be about whether this is a realistic kind of behaviour of isotopes. Should they fractionate one way and then the other way as temperature increases? Okay, so that's something you might want to be critical about if you're analysing this data. Okay, similarly, there's a different relationships up there again. So would we expect that from the theory that we're going to learn today? Okay. So isotopes. So that was basically an introduction to the lecture. That's about why we're interested in learning about isotopes, because it helps us be critical about their use. So start off with oxygen. So just to recap, oxygen has 3 isotopes: oxygen 16, oxygen 17, and oxygen 18. Okay, so what we're going to talk about today is basically variations in the natural abundance of those isotopes. Okay. So first of all, I'm going to talk about this what we call delta notation. So because the variations in the occurrences of different isotopes are actually quite small, so if you were to plot that previous graph for a different sample, it would look very, very similar. So the differences in the amounts of isotopes are very, very small. So what we do is we have this delta notation, which very simply you take the isotope ratio in the sample and you compare that to the isotope ratio in some standard. So down at the bottom here, okay, this is, for instance, the ratio of 18 oxygen to 16 oxygen in the sample, okay, relative to some standard value. Okay, and because this difference, so a ratio of ratios, because that ratio of ratios will almost always be very close to 1, okay, so we're looking at very small differences in the ratio, we basically times that difference by 1,000. Okay, so so this is quite a almost ubiquitous equation in all of isotope geochemistry, okay, because we're describing very small changes in isotope ratio, we use this delta notation. Okay, and the standard that we use on the bottom of that equation depends on what isotope system we're measuring, okay, and sometimes on what we're measuring it in. Okay, so for instance, if we're measuring oxygen isotopes down here, okay, if we're measuring the oxygen 18, so delta 18 oxygen, we would either use what we call a standard called SMO or a standard called PDB. Okay, SMO stands for Standard Mean Ocean Water, and PDB stands for the PD belemnite, which is a belemnite from the PD formation. So what these standards are is that they are basically a pot of substance that's kept in a laboratory and is homogeneous. It has a known isotope ratio, or we just assume that we know the isotope ratio, so that everyone measures their samples relative to that standard. So if I wanted to start measuring, say, lithium isotopes, I would go to the National Bureau of Standards, so lithium isotopes here, I would go to the National Bureau of Standards and I would ask them for a sample of their LSFEC standard, which is just a lithium carbonate, okay, and they would send me that and I would then be able to measure the isotope ratios in that standard and my samples and compare the two so I could calculate the delta values. Okay, and we'll come on to an example of the using different standards in the practical. So there's this table of I guess terminology about what to use when. I mean, don't try and read this now. I mean, I really don't care if you kind of describe something slightly wrong or use delta 13C value or composition, but other people care. Okay, so I mean, have a read through this at your own leisure. But it's really super pedantic. Okay, so we're going to now talk about how and why the isotope ratio in basically one thing might be different to the isotope ratio in another thing. So first thing we've got is this thing called the fractionation factor, which is basically a parameter which describes how different the isotope ratio is in one thing relative to another thing. Okay. So in the example here, we've got this thing at the top here, which is a isotope exchange reaction. Okay, so you'll notice that on both sides of this equation, you've got CO2 and water, and on the other side, you've also got CO2 and water. Okay, so you're not changing the chemistry on either side of the equation, but what you are doing is you're changing the isotopes in each of the species. Okay, so here we've got oxygen 16 in the CO2 and oxygen 18 in the water, and over here you've got oxygen 18 in the CO2 and oxygen 16 in the water. Okay, so what this means is that you've got some CO2 and some water, and you're basically holding those two things together, and you're allowing the oxygen to break off the water and exchange with the CO2. Okay, so you're basically mixing the isotopes between the different phases. Now, in some situations, this doesn't happen. Okay, so or happens very, very slowly. So if you've got, say, for instance, a lump of quartz, okay, and some water, okay, if you just sit those in a container together at room temperature and pressure, you're not going to exchange any isotopes from the quartz into the water, right? Okay, so it's going to take or if there is any exchange, it'll take a very, very long time, millions, if not hundreds of millions of years. Whereas with CO2 and water, you should know that CO2 does actually form a series of chemical reactions with water. Okay, it forms bicarbonate and carbonate and carbonic acid and all those things. So there are reactions that occur that break apart the CO2 and break apart the water so the isotopes can exchange between them. Okay? So, although it looks like nothing's happening on this reaction here, there is actually stuff going on. Okay, so you might remember from chemistry that the equilibrium constant of a reaction is the concentration of the products divided by the concentration of the reactants. The concentration, equilibrium constant of a chemical reaction is the concentration of the reactants divided by the concentration of the products. No. Fuck's sake. There's the concentration of the things on the right-hand side divided by the things on the left-hand side. Yeah? Yeah. Okay. So this is very analogous to the isotope fractionation factor. So the fractionation factor is essentially the same as the equilibrium constant of a reaction. Okay, so it can be described as, if you look over to the, if you were to take the concentration of CO2 18 times the concentration of H2O 16 and divide that by the concentration of CO2 16 divided by the concentration of water with an O18 in it, okay, that would be the same as O18 divided by O16, okay, divided by O18 in the water divided by O16 in the water. So you basically end up with this equation here. Okay, so the fractionation factor is very simply the ratio in one of your things, so in this case the O18 in the CO2 divided by the O18 in the water. The O18, so this equation here. Okay, so the fractionation factor is basically the ratio of isotope ratios. Okay, so it's very often close to 1. So in this example here, if we actually look at the oxygen 18 to oxygen 16 ratio, so there's more oxygen 16 than 18, so the ratio is this guy here, so it's a very small number, and the ratio in water is this number here, so the fractionation factor between them is this number here, which is quite close to 1. Okay, so what this means is that actually, rather than being evenly distributed between the CO2 and the water, the heavy isotope, the O18, preferentially is held in the CO2. Yeah? Okay, so that's the fractionation factor. Okay, but the fractionation factor basically just relates the isotope ratios. Okay, the real isotope ratios in one sample and another. Okay, or one phase and another phase. So we can't actually measure the actual isotope ratio. Okay, all we can measure are these delta values relative to some standard. Okay, so what we actually do when we're looking at, say, two phases, maybe water and CO2, in this case phase A and phase B, so that could be water and CO2 or CO2 and water, no matter which way you do it. Okay, what we can only do is look at the difference between them. Okay? So what we're going to do now is we're going to go and look and see how we can relate the difference in isotope ratios that we can measure, these delta values, how that relates to the fractionation factor. Okay? Okay, so these are basically just rewriting out that per mil equation. Okay? So it's exactly the same. So we've got the ratio. So this would be O18 over O16, perhaps, something like that. In the sample divided by the standard here, minus 1 times 1,000. Okay, you can rearrange that equation to work out what the ratio in the ratio is, and that's what this guy is over here. Okay, and we know that the alpha value, so alpha is the fractionation factor, is the ratio in A divided by the ratio in B. Okay, so that's what this is here. Okay, this bit here and this bit here cancel out to give you this equation here. Okay, so now we have an equation that, there we go. Now we have an equation that relates alpha here to the things that we can measure. Okay. Now, it's some more kind of little mathematical manipulations of this. Okay, so we take one from both sides. That gives us an equation that looks something like that. And then we multiply both sides by this thing on the bottom here. I mean, you can go through these in your own time. They're in your handout. We can then cancel out stuff on the right hand side. That gives us basically gives us the difference in the two the measurements of phase A and phase B. Okay, so that's the thing that we can actually measure, and that equals that thing over on the left. And we can just get alpha on one side now by dividing through by that little term B plus 1,000. Now, the delta values are quite often close to 0. Okay, so it's very rare to have a delta value more than, say, 10. Okay, so what this means is that delta B plus 1,000 is actually quite close to 1,000. So simplify that. So we can simplify that there. So that gives us, so all I've done is said that this number here is very close to 1,000, which gives us this equation here. Okay, now that can be simplified to this. So what I'm saying is this big delta, so this is the capital Greek letter delta, that is essentially what we term the difference in measured isotope, difference in the delta values. So delta A minus delta B is basically just delta, big delta. Okay, so that gives us this equation here. Okay, and we can then convert that into something with a log alpha in it, because alpha minus 1, when alpha is close to 1, is approximately equal to log alpha. Okay, so that gives us this equation here, which actually turns out to be quite useful. Okay, because you might remember from some of the thermodynamics that it's quite often very nice to use the natural log of the equilibrium constant, because that's thermodynamically relevant. Now we have a thermodynamically relevant kind of equation down here that links this delta value here, which is the difference in our two measured isotope ratios as delta values. Okay, that relates to this, basically this fractionation factor alpha. Okay, so we don't have to measure alpha between our two samples. We can just measure their isotope ratios relative to some arbitrary standard. Okay, and that tells us something about the fractionation between those two samples. Okay, so we're going to say a little bit about why isotopes might fractionate. So we know that alpha is not 1, but why isn't it 1, and why is that useful to us? So before we go on, I'll just point out that there are basically two kinds of isotope fractionation, or two kinds of behaviour. This is the same as trace element fractionation in kind of most systems, is that you can either keep everything together, okay, or you could basically isolate the reactants and the products from each other during the reaction. So in this example here, we've got a nice non-low alcohol root beer, and there might be some dissolved gas in the root beer, and then there'll be some dissolved gas in the headspace up here. Okay, and that gas in here can exchange backwards and forwards with the gas dissolved in the beer. Okay, but it's a closed system. The gas can't escape. Okay, so the exchange will happen between those until it's at some equilibrium value. Okay, whereas the gas in the beer that these guys over here are drinking, okay, the gas can escape. Okay, so if we measured the concentration or composition of gas in the headspace above this beer, okay, it might not tell us much about the gas that's actually in the beer. Okay, so there's this on this side over here with the open beer. That's kind of what we would call a kinetic process. Okay, where you're isolating the products of the reaction away from the reactants. Whereas an equilibrium case is where you've kept them together. So in our case, for isotopes, the isotopes can exchange and reach an equilibrium between the two phases. Okay, we'll come on to this. But first, before we go on to describe between the two, we'll talk about chemical bonding. Okay, because chemical bonding is one of the reasons why isotopes fractionate. So, so first of all, you should be comfortable that bonds between atoms behave like springs. So there's basically vibration in those bonds. Okay, and depending on how your molecule is arranged, okay, there might be different types of modes of which they can stretch. Okay, so some bonds vibrate like that, some like this, and all kinds of crazy stuff. Okay, that's not so important at the moment. So the more ways that a molecule can bend and vibrate, that does affect how the isotopes fractionate. But for the moment, we'll just simplify. Well, that's ruined it. It will describe the motion of that ball by going up and down through time. Okay. Now, that waveform through time, that vibration, can be characterized in terms of a frequency. Okay. So the frequency f, okay, is the wave number divided by 2 pi. Okay. And actually, that wave number can be further described as basically it's a property. How that spring vibrates. It's a property of the mechanical properties of that spring. Okay, this basically the spring constant, or Young's modulus, or whatever it is, but the springiness of the spring. Okay, and the weight of the ball on the end of that spring. Okay, so that's what we have over here. Okay, so K is kind of like the spring constant, and M is the mass of the ball. Okay, so as we're on this slide, I'm just going to give you a heads up. So this talk has K, the variable K, 3 times, meaning 3 different things. Okay, so I'll try and remember to point them out as we go along. But K in this case is the bounciness of the spring, and M is the mass of the ball. Moving on also to annoying notations. So frequency F, okay, is also in this talk and in kind of textbooks also V. I have absolutely no idea why anyone would call frequency V, but in many textbooks it's called V. So the wave number is related to frequency by essentially the so frequency is times the speed of light, gives you the wavelength. Okay, so the thing to take home from this side is basically the vibration can be characterized by the spring constant, which is basically a description of how strong the bond is, okay, and the mass on the end of that, the mass of the isotopes on the end of that bond. Now it's a little bit more complicated than that because bonds are not a spring with a ball on the end, they're a spring with a ball on each end. Okay, so this creates a little bit of a mathematical problem. Okay, so we have this term, if we have a ball on both ends of our spring, we have this thing called the reduced mass to take into account that thing. So this reduced mass mu, and that is basically the mass, the product of the 2 masses divided by the sum of the 2 masses. So this is very similar to the gravitational reduced mass problem. Okay, if you're working out little g, okay, you need the mass of the, yeah. So if you have a molecule that's got 3 balls, this becomes ridiculously complicated, like beyond the comprehension of even me, and almost every other person in the university. But anyway, so we have this reduced mass term. It doesn't really matter so much for you guys, but just to point out that mu means mass. Okay, so we can relate the frequency of vibration, okay, to the spring constant, so the bond strength, and the masses of the isotopes. Oh, that's ruined it. The difference between down here and up here. Okay. Now, because you can't actually be at any point on that curve, you can only be at certain quantized levels. So energy and mass are quantized, so you can only go up in small incremental amounts. Okay, so the amount that you can go up are basically these lines. You can only be at these energies. Okay, and the way that those energies are calculated are basically this equation over here. So H is the Planck's constant, which is the amount of energy per each one of these little jumps per kind of atom or per molecule. Okay, so it's a very, very small number. Okay, and it's times the frequency. Okay, so we can work out the energy of basically the first level, okay, by just the Planck's constant times the vibrational frequency divided by 2. And that gives us this energy level here. Okay, very, very simple. And then for each subsequent energy level, we look at basically this equation over here, and it's basically we just N is the number of energy levels. So we're just adding a little bit of quantized energy for each step we go up this kind of ladder of energy. Okay, so there's horrible, horrible maths here. But if we look at, say, for instance, a very, very simple example of hydrogen gas. So this is a hydrogen atom and another hydrogen atom kind of together. Okay, so hydrogen has 3 isotopes. Actually has 4, but it has 3 isotopes. It has hydrogen, which has got a mass of 1. It's got hydrogen that's got a mass of 2, which is called deuterium. It's got hydrogen that's got a mass of 3, which is called tritium. Okay, if we ignore the tritium for now, so if we look at the vibrational frequency of hydrogen bonded to a hydrogen, okay, so that's 1 over 2 pi times K, the spring constant, divided by the reduced mass of hydrogen over hydrogen. Okay, same thing for the deuterium. Okay, reduced mass of deuterium over deuterium. So the ratio of those two vibration frequencies, okay, you can rearrange those two to get this. Okay, which basically turns out is basically related to the square root of the ratio of the reduced masses. Okay, so the vibrational frequency is dependent, or the difference in the vibrational frequency between the two molecules is dependent only on the masses of the isotopes. Okay, so we could actually work that out. So the reduced mass of hydrogen, we bonded with hydrogen, so that's mass 1 times 1 divided by 1 plus 1, that's a half. Okay, and the reduced mass of hydrogen and a deuterium is 1 times 2 over 1 plus 2, which is 2/3. Okay, so you divide those together and you get the ratio of the vibrational frequencies is this. Okay, so it's a number that is not 1. Okay, so there is a difference in the vibrational frequency between the two molecules. Okay, so you can convert that into a change in the energy. So what we're now working out here is basically the difference in the energy between the ground state of hydrogen and hydrogen and the ground states in hydrogen deuterium. Okay, and that is just due to the differences in the masses. Okay, and you can go through that and you can do maths to your heart's content. But for every mole of hydrogen gas that you have, it's a different 3.5 kilojoules difference if you wanted to break those bonds apart. If it was hydrogen or hydrogen deuterium. Okay, so this is important because it means that if you have to want to break that bond, if you're doing a reaction that involves breaking that bond, okay, then it'll be easier to break the hydrogen-hydrogen bond than it is the hydrogen-deuterium bond, because it's lower down in its kind of little potential well. Okay, so if we look at how this comes to relate to isotope fractionation in the equilibrium isotope fractionation case. So this is kind of quite a special case because we're going to use a reaction where the alpha, the fractionation factor, is nowhere near 1. Okay, so it's a reaction that takes water and hydrogen sulfide. So this is H2S, but with one of the H's replaced with a deuterium, and this is water, HDO, with one of the hydrogen in the water replaced with a deuterium. Okay, so we could work out the alpha from the concentrations of those different species there, which is essentially looking at the deuterium to hydrogen ratio in water divided by the deuterium to hydrogen ratio in hydrogen sulfide. So in most isotope exchange reactions, this is quite close to 1. Okay? But in this case, there's a really big isotope fractionation difference. Okay? It's 2.35, which is a huge isotope fractionation. And part of the reason for that huge isotope fractionations is because the relative mass difference between hydrogen and deuterium is very large. So in the example before, we were looking at the difference between calcium 44 and calcium 40. Okay, so that's maybe a 10% difference in mass. Okay, the difference in mass between hydrogen and deuterium is 100%. Okay, yeah, mass difference between 1 and 2 is 100%. Right, so it's very much different. Okay, so one of the questions you might ask is, what's driving this difference? So if we left this liquid and this gas together for a long time, they exchanged all of their isotopes until they reached equilibrium, okay, and they were not evenly distributed, what is it that's driving that change in distribution of isotopes? Okay, so if we go back to the analogy that this is like an equilibrium constant, okay, so alpha is kind of like K, the equilibrium constant. This is the second time K is mentioned. Okay, that's something that is not. So first spring, now equilibrium constant. So you might remember from the thermodynamics that there's a relationship between the equilibrium constant of a reaction and delta G, the free energy of that reaction. I'm getting lots of blank faces. Jeff should have done this with you a couple of weeks ago. Doesn't matter. But there is a relationship. So delta G is the free energy of the reaction. Log K, this is why we used that equation before with the log in it. Okay, log K is the equilibrium constant. So if log K is not equal to 0, okay, that means that delta G must not be 0 for this isotope exchange equation. So there must be something that is driving that isotope exchange reaction. Okay, there must be something. Okay, and that delta G comes from this difference in the ground states of the atoms from their vibrational frequency, which is due to their mass. Okay, so delta G is, we're basically looking at, of the reaction, is the difference between up here and down here. Okay, but for the different isotopes, they're different amounts. Okay, from here to here and from here to here, it's different for different isotopes. Okay, that delta G, because of the differences in energy levels, okay, causes there to be something that's driving that isotope exchange reaction to favour heavier isotopes in one of the species. Okay, so as a rule, the heavier isotopes, okay, go into the phase, the chemical species that has the biggest change in energy. Okay, so you can see here that the heavier isotopes will be going in here into the water, because there's a bigger difference from water to HDO, from hydrogen sulfides to HDS. Okay, so heavier isotopes basically go into the bond that has the biggest difference in 0 point energy, the biggest difference in the ground state of that bond due to the mass difference. Okay, so what this means is that this is basically a diagram that shows two different bonds of different strengths. Okay, so this at the top here. This is a weak bond. This is a strong bond because it takes more energy to get from here to break the bond than it does to get from here to break this bond. Okay, and if you just look at this graphically, the difference between this point here and this point here, okay, is less than this difference from here down to here. Yeah? So this is a bigger jump. Okay, so this means that it causes there to be a bigger delta E, so a bigger energy difference between the two molecules that have got different isotopes in the stronger bond. Okay, so the key point is the heavy isotopes preferentially will go into the stronger bonds. Okay, if they've reached equilibrium. Okay, so because this reaction, this isotope preference, okay, is driven by delta G, okay, free energy, and we know that delta G is made up of some enthalpy and entropy. Yeah? Okay, there's also a volume term in this, but the volume of different isotope species is always the same. Okay, so there's no delta V term. So this delta H here, that's the effect that I've just described. Okay, so that's the difference in energy caused by the difference in ground states because of the different masses. So the delta S is the entropy of mixing, which you've done with Jeff. Yes. So if you separate out kind of all your isotopes, so all of the oxygen 18 over here, all of the oxygen 16 over here, that's ordered. Okay, you've added order to the system. Okay, so that's bad for entropy. So as you increase the temperature, separating out the isotopes into different pots, okay, doing this isotope fractionation costs you thermodynamic delta Gs, okay, because it likes at higher temperatures things like to be mixed. Okay, so this means that there's a temperature dependency on that isotope fractionation, because at low temperatures the isotopes want to be separated out into their different phases where they want to be because of the basically enthalpy of the isotope fractionation. But at higher temperatures you've got this mixing, so everything wants to be mixed. So you can basically approximate that relationship using an equation like this, where you've got the fractionation factor is dependent on the inverse of the temperature. Okay, and there are some constants in there. Okay, you don't need to worry about those for now. But so as the temperature gets bigger, the isotope fractionation gets smaller. Okay, and there's a slightly different relationship when you get to very high temperatures. You tend to get this T squared relationship. I have absolutely no idea why they're different, but that doesn't really matter. All you need to know is that it's a temperature dependence on the amount of fractionation that you have. Okay, and that is due to the enthalpy of mixing. Entropy of mixing. Idiot. Okay. Okay, and this is essentially one of the reasons why isotopes are really useful. So if we can measure alpha, so if we can measure the isotope difference between two phases, okay, we know that should be dependent on temperature if those two phases were allowed to reach isotopic equilibrium. So if they were held together for long enough for the isotopes to exchange, okay, then that exchange will be playing off against the temperature effect of mixing. Okay, so I mean this example here, I mean a whole bunch of different minerals that occur in magmatic and ore hydrothermal systems. So when quartz and magnetite basically grow together, so these are two solid phases. Okay, so it's very hard to achieve isotopic equilibrium between them because isotopes has to go out of the quartz into the magnetite. So when we talk about isotopic equilibrium here, we basically these two phases, if they grew at the same time from the same liquid, so the liquid as they were precipitating could allow the isotopes from one to the other to be mixed. Okay, so here we can use that. So that's so this is the axis along the bottom. This is 1,000,000 divided by temperature squared. So high temperatures, okay, are over to the left. Low temperatures are over to the right. Okay, and then on this graph here we've got log 1,000 log alpha. Okay, so that means that we've got bigger isotopic fractionations as you go up. Okay, so you can see that basically for different mineral systems you have different temperature relationships to the amount of isotopic fractionation. Okay, which means if we could go out, we find some hydrothermal system, we measure the isotope ratios in different minerals, we can work out what temperature they precipitated. But only if we assume that they precipitated at isotopic equilibrium with each other. Okay, so for stable isotope systems, we've got to think what makes for good isotopic fractionation. So if you've got a large difference between them, okay, where it says element tends to form highly covalent bonds, this is that K term, the first K, not the second K, the strength of the bond. Okay, if you've got a very strong bond, that means the effect of the mass becomes greater. And then basically if you're doing reactions that have got very, very different bond strengths on either side of the equation, that can lead to a large isotopic fractionation. Okay, so moving on to kinetic isotope fractionation. So this is where basically you haven't got something, you're not keeping the reactants and the products together. So the reason why you might get fraction here is because the stuff is literally moving around. Okay, so in a case here we're looking at maybe some gas atoms moving around in a box, and the speed at which they move around, okay, is dependent on their mass, because each of those atoms should have a similar kinetic energy. I mean, kinetic energy is half mv squared. Okay, so the more mass you have for the same kinetic energy, you'll be moving slower. Okay, so if we look at like an example here, we can see that I think this is for CO2. If you've got a CO2 that's got carbon 13 in or carbon 12 in, the one with carbon 12 in can diffuse 1% faster than the one with carbon 13 in, because it's a lighter molecule, so it can move faster. So if you had a process that involved diffusion, okay, that can impart an isotopic fractionation, because the product, okay, of that will be enriched in the lighter isotope, because it can diffuse there faster. Okay, so kinetic isotopes tends to form, obviously you get, there's basically that moving aspect of the fractionation, but also from the bond strength. So the bonds formed with lighter isotopes are weaker. Okay, so that means that they're easier to break. So if you're doing a reaction and you allow it to reach equilibrium, you allow the reaction to finish, it doesn't matter whether one bond was easier to break or the other, okay, because you'll reach that final equilibrium isotope fractionation. But what if you say you stopped the reaction halfway through? Okay, the bonds that were easier to break would have been broken first, so your product would then be enriched in those lighter isotopes. Okay, so with kinetic isotope fractionation, if you're doing a reaction that doesn't go to completion, then you end up with an isotope fractionation. Now there are also reactions which, so the reactions I've showed you before, they go both ways. So like for instance CO2 dissolving in water, you can dissolve it in water and then it can come back out of the water. Okay? Not all chemical reactions are bidirectional like that. Some chemical reactions only go one way. Okay? An example down the bottom is photosynthesis. So photosynthesis only goes one way. Okay? There's no reverse reaction to photosynthesis. Respiration is not the opposite of photosynthesis. Okay? It's not. It's a completely separate reaction pathway. Okay? So if you are doing photosynthesis, if you were a plant, okay, the reaction at the top here, carbon 12 in the CO2, that reaction will go faster than the reaction at the bottom, carbon 13 to CO2. So that means that if you are making something, if your product, your sugar, then would be enriched in the carbon 12. Now, this is quite important because this allows us to kind of start to produce different reservoirs on Earth that have got different isotope ratios. Okay, so these are a whole bunch of different things on Earth that have got different isotope ratios. Okay, so if we just look at some of those, if we just look at, say, for instance, so the ocean has got a value around 0. Okay, and then things that grow from photosynthesis here, they've got lighter isotopes, so they're depleted in the carbon 13, and they've got more carbon 12 in. Okay, so they've got negative delta values. Okay, and that's because they've basically been produced by photosynthesis. Okay, which favours, so basically anything that life does with any isotope system will always favour the lighter isotope. Okay, and then if you took this carbon from these plants here, and then you maybe did another kind of action on those, maybe you respired those, or you had some fungi that kind of ate them and then gave out methane. Okay, that methane that's given out, okay, would be even lighter. Okay, down here. Okay, so this basically allows us to start to trace gives different reservoirs of carbon dioxide or carbon, different isotope values. So this is quite full. So for instance, as an example, if we were to burn fossil fuels, what would happen to the carbon-13 of the atmosphere? Okay, so I want people who thinks the carbon-13 of the atmosphere will go up to put their hands up if we burn fossil fuels. And who thinks the delta 13C of the atmosphere will go down if we burn fossil fuels? And okay, so if we have, okay, so the people who put their hands up second were obviously the people that were reading ahead and have this slide in their handouts. So we can see here that as we've been, so this the pink curve down here is us burning fossil fuels throughout the last couple of years. Okay, and this at the top, the blue, is the delta 13C. Okay, and you can see here that we've got negative values, but it's becoming more negative. Okay, so we're taking out, we're adding in carbon-13 to the atmosphere preferentially. Okay, and you can read into the details about the ups and downs and stuff like that. Okay, so similar example here. So if we're if we make the oceans go anoxic by burning lots of fossil fuels and causing ocean stratification and eutrophication, or there was some ocean anoxic event in the past, if we did that, then we would increase the burial of organic carbon, because if there's no oxygen in the oceans, that organic matter can't be respired. Okay, so what will happen to the carbon-13 of marine carbonates? So marine carbonates are produced from the remaining carbon in the ocean, so the stuff that's left over from the production of organic material. So who thinks it'll go up? More positive. Who thinks it'll go down? Who hasn't looked at the next slide? Okay, so this is an example from, I think, the Jurassic. So this is an ocean anoxic event. So you can see lots and lots of limestone being deposited here. And then we get to this kind of layer here where we get lots of black shales deposited. So the ocean becomes anoxic, and all of the organic material gets deposited on the seafloor rather than being respired. Okay, so what we can see here is over on the left-hand side, this is the carbon isotope rate record of marine carbonate this time. So this is basically the carbonate that's produced from the dissolved inorganic pool. So time is going up. So we start off here at 2.5. Then as we enter this ocean anoxic zone, okay, we start to increase our delta 13C. Okay, so it goes up and then only starts to come back down again once we've exited this period of oceanoxia. So what's happening here is we're taking organic matter out of the ocean, which has got a light isotopic composition. We're storing that in sediments. So that means that the carbon that's left in the ocean must be heavy, must be more enriched in the carbon-13. Okay, reaction rate. So this is the third time K will be mentioned here. So in this times K, reaction rate this is kind of the Arrhenius relationship type thing. So some constant times e to the power of basically the activation energy. Okay, divided by K twice in the same equation. Do different things. This is the equilibrium constant divided times by temperature. So basically, how fast reactions go, okay, is dependent on this activation energy here. Okay, so this is this distance from here to here, which is different for different isotopes. Okay, which means that the reaction rate is dependent on the isotopes. So this is another reason why kinetic processes, okay, reactions that haven't finished, will cause there to be isotope fractionations, because the reaction rate is dependent on the mass of the isotopes involved in that bond. Okay, so we're going to kind of go on to an example now of how this whole fiasco works with water. Okay, so first of all, you should remember that with any isotope fractionation system, well, if it's an equilibrium, the heavier isotope goes into the stronger bonded environment. Okay, so what we're going to be talking about now is water and water vapor. Hello. So with water and water vapor, the stronger bonded environment is the water, okay? Because in addition to, so that the water molecule is exactly the same, okay? But in water, there are hydrogen bonds that bond between the molecules. So that adds to the overall bond strength, okay? So what this means is that if we had a box with some water in it and some water vapor in the space above that, and that was sealed and stuff couldn't get in or out, the isotope ratios in the isotope ratios of oxygen 18 to 16 would be 9 per mil, so 9 parts per thousand, lighter, okay, so more oxygen 16 in the water vapor than it is in the water, okay? So that's the case if it's kind of like, if we keep it in a box, but the world is not like a box, right? So if you're evaporating water out of, say, the ocean, okay, that water vapor gets moved away from the surface of the ocean quite quickly by the wind, okay? So that leads to a little bit of extra fractionation, okay, because the lighter isotope, oxygen 16, evaporates a little bit faster, okay? So if you go on to learn, this is what the YouTube video is about. It looks like it's for kids, but it's not. Well, it's not like it's not for kids, but it's anyway. So let's have a look at what happens if we to the isotope ratios if we imagine this situation, we keep it in the box, or we allow the water to be moved, the water vapor to be moved away. Okay, so rather than looking at evaporation, we're going to look at condensation, which is exactly basically the opposite process. Okay, so some maths first. So basically, if we just look at the total amount of water, okay, is essentially the same as the total amount of water with a 16 on it, because the O18 is very rare. Okay, so let the amount of O16 water be A and the amount of O18 water be B. Okay, so the rate at which that happens is basically the rate of change of those amounts of stuff. Okay, so the fractionation factor, okay, is just the ratio of those two rates. Okay, because if the oxygen 16 is evaporating faster, okay, so than the oxygen 18, then that will cause there to be a fractionation. Okay, so the ratio of those two rates is the same as the ratio of the isotopes. Okay, so that gives us this guy here, okay, which we can kind of rearrange and whatnot to get all this stuff down here. But you can work through these maths at your own leisure. But essentially what I'm trying to get to is you end up with these equations here, which should be familiar to you from the elemental fractionation, when you're looking at trace element fractionation in kind of magmatic systems or whatnot. So the key thing is that so F here is the amount of stuff that has evaporated or condensed. Okay, so if it's 0, everything is in the water vapor. You've got all water vapor. If it's 1, all of your water vapor has condensed and you've just got water. Okay, alpha is the fractionation factor between water and the vapor, so that's kind of 13 per mil, or 1.013. Okay, and that then this is the amount of the light isotope. Sorry, this is the amount of the heavy isotope, oxygen 18 over oxygen 16. The amount, okay, divided by the amount that you had at the beginning. And this might look quite similar to you. So this is, if we assume that the amount that you had at the beginning is kind of like the standard. Okay, so if we assume that our standard had an isotope ratio of 0, by kind of definition, if you measure the isotope ratio difference between a standard and a sample in delta notation, it would be 0. Then that this bit here, this is essentially like the per mil equation. So here, so we start here. If we took that water vapor and condensed it all, okay, we'd move to here, and we'd finish with exactly the same isotope ratio than we started with. Because all we've done is we've taken everything out of one phase and we've moved it all into the other phase. Okay, so you couldn't have fractionated the isotopes. Okay? Now, if we look at what happens as we do that, Okay, so first of all, so if we started condensing, okay, we started producing some water out of this water vapor. Okay, this up here would be where our condensate would be. Okay, so it's got heavier isotopes than the vapor. Okay, and if we carried on condensing out of that kind of cloud of vapor, okay, we would be removing water vapor at this value. Okay, that would make the remaining, so we'd be removing basically water of this value, which would leave the remaining vapor a little bit depleted. Okay, so as we carry on, we move along this red line. Okay, and we're gradually removing the heavy isotopes into the water and leaving the lighter isotopes behind in the vapor. Okay, so if we kept it in a closed system, okay, we'd follow these red lines where basically our condensate would start out up here, but then by the time that we'd condensed everything, we'd end up here. Okay, and that's basically following this reaction down at the bottom. Okay, now let's imagine what would happen if we had basically a hole in the bottom of our box. Okay, so we had a box full of water vapor, and if we condensed some water out of that, but then we lost that condensate out of the bottom. Okay, so the first thing would happen, we start here with all vapor, and we condense a little bit of water out of that. Okay, and then that would start to drive our remaining vapor to lighter isotope values. Okay, but the problem is, well, it's not a problem, but the difference is that this water, okay, so the red line is basically all of the water in the box that we've condensed. The blue line is the instantaneous condensate, because we keep on throwing it away out of the bottom of the box. Okay, so that means that because we keep on throwing it away, it can't exchange back with the water vapor to keep the isotope ratio of the water vapor along this red line. So because we're removing from the box heavier isotopes in the condensate, the total isotope value of the box, the vapor plus the liquid, gets lighter as we continue to remove water vapor. Okay, as condensate. So that means as we move along here, we start to follow this blue line, which, because when we get to this point, we've thrown away most of the water. Okay, we've condensed it out of the water vapor phase, it's formed liquid, and then that's gone away. Okay, so that's removed throughout. We've gone from here to here, we've been removing the heavy isotope, leaving us only with the lighter isotopes remaining. Okay, now this is important because this would happen on that slide. Well, this is what happens in the world, okay, with rain. So the ocean here has got a delta 18O of 0. And it's got a delta 18O of 0 because the standard, which we measure oxygen isotopes against in water, is called standard mean ocean water. Okay, so it's got an isotope composition that's supposed to be equivalent to the mean ocean. Okay, so there's some variability in the ocean, and we'll come on to that in practical, but it should be around 0. Okay, so you evaporate water from the ocean, and that forms water vapor over the ocean, and that's lighter. Okay, so it's enriched in the light isotope, so the delta 18O is negative. Okay, so it's got more oxygen 16 than 18 than it would have if it was in the ocean. Now, that water vapor forms clouds, okay, and when those clouds rain out over land, okay, they're removing the heavy isotope from the cloud because the heavy isotopes preferentially go into condensation, into the condensate. So that makes the cloud even lighter. Okay, so the more rain rains out of your cloud, okay, the lighter the isotopes in your cloud are. Okay, which means that as you progress away from a coastline, you should get progressively more negative delta O18. Okay, so as water evaporates from, say, the North Atlantic, comes across over Scotland, so if we were to measure the oxygen isotope composition in rainfall, okay, it would be more negative in Edinburgh than it is in Glasgow because the heavier isotopes have rained out over Glasgow. Okay, So this is important in all aspects of, well, not all, but many aspects of geosciences, particularly in ice cores and ice sheets, because this, imagine up here, this is an ice cap, okay? So the amount, and this is near the equator, okay? Water evaporates near the equator, and as it moves towards the poles, this has a really big effect on the, basically the isotope ratio of precipitation in ice sheets, okay? And we can use those isotope ratios to reconstruct all kinds of things about the amount of precipitation that's happened in the past and the temperature and all kinds of things like that. Okay, so that's isotope fractionation. There's lots of bullet points on there which you can kind of read in your own leisure. Okay, so I think right. So just to go back to this slide that we started on. Okay, so if we're going to be really super critical about this now. Okay, so first of all, our error bars on here are bigger than the variation. Okay, so that flags us up for a bit of a question. And then there's this question, should the isotope ratio change with temperature? Okay, and I think hopefully you'll agree that there should be a relationship between the isotope fractionation and temperature. Okay, but it should not go up and then down. Okay. So we don't know whether it should go up or should go down because we don't know what the delta... This is not alpha, this is not the fractionation factor. This is just the measurement of the carbonate. So we don't know what the delta 4440 of calcium is in dissolved calcium in the ocean. Okay? So we don't actually know whether this should go up or down. Okay? But if we did, we should at higher temperatures, the fractionation should be smaller. So the difference between the water and the carbonate should be smaller as we go to higher temperatures. But what it shouldn't do is change its direction of fractionation as you change the temperature. Okay? So those are kind of some of the things that you should be looking at when you're looking at isotope data. Okay, right.